In this lesson, we'll talk about integer exponents. Let's recall the definition of power. Power is really a shorter notation of multiplication. If we multiply the same item, in this case x, n times, then to record this multiplication in a shorter way, we use nth degree power. X to the n tells us that we need to multiply x by itself n times. In this notation, x will be called the base and n is the exponent. The overall thing, x to the n, is the nth power of x. Let's recall exponential rules. To multiply powers with the same bases, it's enough to keep the base and add the exponents. So multiplication of powers translates into addition on exponential level. Why it is so? Well, we can try a simple example like 2 to the 2 times 2 to the 3. This tells us to take two 2's, 2 times 2, and multiply it by 3 2's. So we really multiply 5 times the same 2. We multiply the 2 times, and then 3 more times. So we are adding the 2 plus 3, therefore this is 2 to the 5. I assume we already know those rules. This is just quick recollection. Okay, similar rule applies to division of powers with the same bases. We keep the base and we subtract exponents. So division translates into subtraction on exponential level. Again, we can justify this using a simple example like 2 to the 5 over 2 to the 3 and see what will happen. 2 to the 5 really means that I need to multiply 2 by itself 5 times. 2 to the 3, I have 3 2's in the bottom. And now I can reduce common factors, so 2 from the denominator and 2 from the numerator, and again, and again. So really what we've done is, from 5 2's, we took away 3 2's. So it was 2 to the 5 minus 3, which is indeed 2 to the 2. Obviously, this is just one example that justifies why this rule works. But you can imagine that for any other number, as long as the bases are the same, the procedure will be the same. Because of the cancelling of the same many items in the bottom and in the top, the division of powers really translates into subtraction on exponential level. The next rule is, when we take power to the power, it translates into multiplication on exponential level. So powers translates into multiplication. And this could be justified by a simple example as before. For instance, if I take 2 to the 3 and then raise it to the 2, that really means that I have to take twice the group of 2 to the 3. So 2 to the 3 times 2 to the 3. But each 2 to the 3 represents 3 2's, and another group, 3 2's. So altogether, we really have 2 to the 6, which is the same as 3 times 2. 2 to the 3 times 2, which is 2 to the 6. Okay? The next rule is, we can distribute the exponent to every factor in the bracket. So, for example, if I have 2 times 3 and it's raised to the square, that really means the same as 2 times 3, one bracket, times another bracket. There is 2 of the same type of brackets. But since multiplication is commutative, we can switch the order of 2 and 3. So we could actually write this as 2 times 2 times 3 times 3, which indeed becomes 2 square times 3 square. So yes, we can distribute the exponent inside the bracket as a power of each factor. Similarly, we can distribute the exponent over the division. So a over b to the n is the same as a to the n over b to the n. To see it on particular example, well, let's take 2 over 3 and raise it to the square. That really means the same as 2/3 times 2/3. But it could be written as 2 times 2 over 3 times 3, which is the same as 2 square over 3 square. So yes, indeed, we can distribute the exponent to the numerator and denominator. The next rule tells us that anything raised to the 0 is actually equal to 1. Obviously, this anything can't be 0. 0 to 0 is undefined. We have no idea how much is 0 to 0. However, how to justify that anything to 0 is equal to 1? Well, let's think. If I will take expression a to the n over a to the n, well, since I divide the same value by itself, then this must be equal to 1. On the other hand, using the rule about division of powers with the same basis, we can rewrite this quotient as a power of a. What power of a? N minus n. But n minus n is actually 0, so yes, indeed, a to the 0 must be equal to 1. Obviously, this kind of thinking can't be performed if a is 0, because we wouldn't be able to divide by 0. So 0 to the 0 is undefined. Couple more rules. A negative exponent, a to the negative 1, is defined to be 1 over a. So the negative exponent causes that the base travels to the denominator, or other words, that we're going to take reciprocal of the base. Again, this rule works as long as a is not 0, because otherwise we wouldn't be able to divide. The consequence of this rule, together with the power to the power rule, is that a to the negative n is the same as 1 over a to the n. How come? Because a to the negative n can be seen as a to the negative 1 and then to the n. Remember, power to the power multiply exponents, so this will be the same as negative n. However, a to the negative 1 is 1 over a, so instead of this base, we can write 1 over a, everything to the n. But then, using the rule about distributing the exponent to the numerator and denominator, 1 to the n is the same as 1, and a to the n stays. So overall, a to the negative n is really equal 1 over a to the n, which means anytime you want to get rid of the negative on exponential level, it's enough to bring the base to the denominator. Or, if it was in the denominator, it's enough to bring it to the numerator, which really means switch the level. To change the sign by the exponent, switch the level from numerator to denominator, or the other way around from denominator to the numerator. The following consequence of those rules is, if we have a fraction a over b to the negative exponent, remember, to get rid of negative by the exponent, it's enough to take reciprocal of the base. So a over b to negative n is the same as b over a to the n. Again, in both cases, we need to protect denominators. So here a is different than 0. Over there, both a and b have to be different than 0. And finally, our fraction could be written in that form, a to negative n over b to the negative m. Notice that this is exactly the same as the left-hand side in the previous case. So, since to annihilate this negative is enough to switch the level, a to the n goes down, and then the negative in exponent becomes positive. And similarly with b to the negative m, that goes up. To switch negative exponent to positive exponent, change the level from numerator to denominator and otherwise. Notice that this is exactly the same as the right-hand side of the previous equation. Again, a and b must be different than 0 here. Okay, let's practice using those rules. We'll have a bunch of examples. We want to simplify them and leave the answer with positive exponents only. Also, I would suggest to avoid evaluating large numbers. So for example, if you have 2 to the 50, don't bother to evaluate this. It's better to leave it as 2 to the 50. I would say stick with the rule that if after evaluating the number is reasonably small, for example within 100, then you're okay to evaluate. Other than that, it's better to leave as a power of prime number. So if I will have 2 to the 2, I'm okay to evaluate and say it 4. But if I have 2 to the 50, I would definitely stay with 2 to the 50. So leave the answers as powers of prime numbers. Another reason why this is more useful is because in larger calculations, sometimes we may have powers of 2 in the denominator, for example 48 here, and then it will be a lot easier to reduce them, rather than evaluating each number, which is very, very large, and bothering with division. So keep in mind, leaving numbers as powers of prime numbers is usually more beneficial. Okay, how can we simplify this expression? First of all, we need to realize what kind of operation we deal with. Well, between 3 and x squared, there is an invisible multiplication. Also, between x squared and a bracket, there is a multiplication. Negative 5 and x to the negative 5. Oh, there is another multiplication here. Is this bracket essential here? Well, yes, it is, because we need to disjoin two operations in a row, this multiplication and this subtraction. But this bracket is actually essential only because of the negative 5. If this number would be 5, we wouldn't have to use a bracket at all. So please be careful and don't be misled by this negative sign here. We don't have any distribution because we still have one term within the bracket. Okay, if I want to release this bracket, I really multiply one term by one term, which means first let's multiply numerical values. 3 times negative 5 is negative 15, and then we multiply powers. But remember, when we multiply powers, we add exponents. So it will be x to the 2 minus 5. So it's negative 3. Since we're supposed to leave the answer with positive exponents, let's bring this x to the denominator and make the exponent positive. So negative 15 stays in the numerator. Only x will go to the denominator with exponent positive 3. Remember, the exponent refers to the immediate letter or number, or anything that's in a bracket. We didn't have anything in the bracket, so negative 3 refers only to the x. It does not refer to negative 15. So this negative 15 stays in the numerator where it was. Also, this minus has completely different role than that minus. This is a negative 15 as a number, and this negative in exponent causes switching the level of the whole power to the denominator. Okay, let's see the second example. Here we have a subtraction of two terms. The first term is 1, so let's copy it. Then we have a minus, and how much is something to 0? Remember, anything to 0 is really equal to 1. So 1 minus 1 is a nice big 0 with a happy face. Okay, let's try some other examples. Here we really need to be careful. We don't have any bracket around negative 5, therefore the exponent negative 2 refers only to the 5. It has nothing to do with this minus. So keep the minus and then think about 5 to the negative 2. To make the exponent positive, we move 5 to the denominator. 5 to the 2 goes here, and what's in the numerator? Nothing. But nothing for multiplication really means 1. Don't forget to write numerator here. Okay, therefore this is negative 1 over 25. Next one. Well, this example is very similar to that one. However, there is an x before the exponent negative 2. So this negative 2 refers only to the x. It does not refer to negative 5. Therefore, negative 5 stays. That will go into numerator. And x to the negative 2 becomes x to the 2 when we move it to the denominator. So that would be the final expression. And another example. This time we have a bracket, so this exponent negative 2 refers to the whole bracket. Therefore, the whole bracket needs to travel to the denominator, and it will be still raised to the exponent, but positive 2. What's in the numerator? Nothing. That means 1. This simplifies to 1 over, and then negative 5 when squared becomes positive. So we can write either positive 25 or 5 squared without the negative anymore, and x squared. So that would be the final answer. And another interesting example. This time we have lots of negative 1 exponents. Let's see what are we actually dealing with. Let's rewrite every single number with no negative exponent. So 2 to the negative 1 is the same as 1/2. 3 to the negative 1 is the same as 1/3. And 4 to the negative 1 is the same as 1/4. So we really have a complex fraction problem here. And everything, in the end, will be raised to negative 1. Okay, in order to simplify this complex fraction, we can do a couple things. We can just simply add the two fractional numbers in the big numerator and then change the main division into multiplication of reciprocal, or we could multiply the top and the bottom of this big fraction by LCD of 2, 3, and 4. Since those fractions are not too difficult, maybe just add them as they are. So the common denominator would be 6, and then to bring 1/2 to the denominator 6, we need to multiply the top and the bottom by 3. So it will be 3. Plus, to bring 1/3 to the 6's, well, that will be multiply top and the bottom by 2. So plus 2 over 1/4. Everything in the end needs to be raised to the -1. Okay, now in order to simplify this complex fraction, I'm going to rewrite the big numerator as 5, 6, and then change this main division bar into multiplication by the reciprocal of the denominator. So reciprocal of 1/4 is just 4 over 1, or 4. Then after we perform this multiplication, everything will be raised to -1. So now it's good time to reduce. We can reduce 4 with 6, because 4 belongs to the numerator. So divide by 2. That leaves us 2 here and 3 over there. And finally multiply. 2 times 5 is 10, and 3 in the denominator, everything raised to the -1. So finally that becomes 3/10 as a fraction, or it's also easy to convert it to decimal, 0.3. That's our final answer. It doesn't matter if we leave it in a common fraction form or a decimal form. Let's see another example. Here we have a quotient of 2 powers with the same basis. Well, let's use the rule keep the base and subtract exponents. But we need to be careful because we deal with negative exponents already. So, nice and slowly. -6, then minus because of the division bar, and we are subtracting -15. So we need to put a bracket here to disjoin these two negatives. Okay, so the whole calculation really translates into addition or subtraction on exponential level. Therefore, we have 5 to the, and the exponent is -6 plus 15. So 15 minus 6 is actually 9. 5 to the 9. And we don't need to evaluate this. Let's leave it as it is, 5 to the 9. Finally, let's simplify this expression. So what should we do here is to deliver those exponents to every factor in the bracket. -2 square. Okay, let's write it down, -2, but remember to put a bracket. We are not squaring just 2, we are also squaring the negative, because it was inside the bracket. So the exponent 2 refers to it. Then it's a square, and then it's b cubed, and it also will be squared. So power to the power, what do? Multiply exponents. b to the 6 times. I need to distribute the -3 to every single factor. However, since I know that 4 is a power of 2, and in the future it may be combined with this power of 2, let's rewrite 4 as a 2 square first. So that's our 4, 2 square. But then we have to raise it to -3. Therefore, put a bracket to the -3 in the future. And go on, b to the -3 over a to the -3. Great. So now let's go to the next line. We know that negative to the even exponent becomes positive. So -2 square is the same as 2 square. Since everything is multiplied in the numerator, maybe first write all numerical values and then letters. So 2 to the 2 and to the -3, we multiply exponents, so it's 2 to the -6. Let's write it down, 2 to the -6. And then it's a square and b to the -3 over, in the bottom, let's maybe start in alphabetical order, a to the -3 and b to the 6. Great, now what we can do, we can combine powers with the same basis. So 2 to the 2 times 2 to the -6, we add exponents, so it will be 2 to the -6 plus 2 is -4. Since we don't like to keep powers with the negative exponents, let's switch the level. That means the b cubed will go down with the positive exponent, and the a cube will go up with the positive exponent. So we can write copy the a square, and this a cube will go up, copy the b to the 6, and the b to the negative 3 becomes b to the 3 in the denominator. So overall we have a squared times a cube is a to the add exponent, so it's 5. Now this 2 to the negative 4 can be written in the bottom is 2 to the 4. And b to the 6 times b to the 3 add exponent, so it's b to the 9. So that's the final answer. If you want to, it's okay to write a to the 5 over 16 b to the 9, but it's not necessary to evaluate this 2 to the 4. So the answer can be left this way or that way, doesn't matter. Couple more examples, more work to do. You may want to stop the video and try those examples on your own first, and then come back to check. If the question is as big as this one, there's many roads that you can take and come to the same correct answer. However, my suggestion would be as follows. If you have a big expression in a bracket, first of all get rid of all negative exponents within the bracket, collect powers with the same basis, and then finally at the end apply this negative exponent from the outside. So let's try to get rid of negative exponents inside by switching the levels. So this y to the negative 2 will go down and x to the negative 6 will go up. Other powers will stay where they are. Also, we could reduce the coefficients. For example, this 3 can be reduced with 15, leaving us with 5 in the bottom. So what do we have? We have negative, we have x to the 4, the y to the negative 2 goes down, so it will be recorded in the denominator somewhere here, y to the 2. The y to the 5 stays as it was, because it was positive, so it stays. The x to the negative 6 travels up and becomes x to the 6, and the bottom had 5. Well, looks a lot simpler already. Now everything to the negative 3. Next step, collect powers with the same basis. So we have negative x to the, and we add exponents, so it's x to the 10 over 5 y to the 7. Everything to the negative 3. Now it's time to apply this negative exponent from the outside. Okay, let's do one step at a time. To drop this negative, we need to flip the base, take reciprocal of it. So that would be equal 5y to the 7 over negative x to the 10, and then we still raise it, but we raise it to the positive. So again, this negative causes taking reciprocal of the base, or switching levels, which is really the same. Finally, we deliver this exponent 3 to every single factor. So 5 to the 3 is 5 to the 3, or 125. Y to the 7 to the 3, we multiply exponents, so y to the 21, over negative to the odd power is negative, and x to the 10 and to the 3 is to the 30. Final answer. And another big example. I really encourage you to try on your own and see if you haven't done any mistake on this one. So the first suggestion would be reduce the coefficients. 208. That's 1. And 200 divided by 8 is 25. Okay, so let's write negative, and instead of 25, let's write 5 square. Then copy the x cube because it has positive exponent. Bring the y to the negative 7 up to make it positive. And this power will go down to the denominator. So we have x5, and then we have y to the 5. Shift the levels whenever you have negative exponent. If the exponent is positive, keep it at the same place. And then everything to the negative 4. So now let's simplify powers with the same basis. For example, if we have 3 x's in the top and 5 x's in the bottom, we can reduce 3 x's from the top and from the bottom. So I cross out this x to the cube entirely, but in the bottom I don't cross out the whole thing, I just cross out the 5. The 5 minus 3 becomes 2, so the remaining power in the bottom will be x squared. Similarly here, y to the 7 and y to the 5, I can reduce 5y's from the bottom with 5y's in the top, leaving me y square in the top. Okay, let's rewrite nice and clean. It will be negative 5 square, and then the x cube is totally gone, and here I have y square. In the bottom, I have x square and the y is gone, so just x square. Everything is raised to negative 4, and we'll go to the next line. So now we're ready to take care of this negative from the outside exponent. That causes switching the level of the entire fraction, so reciprocate. X squared over negative 5 square y square, and then everything is still raised to the 4. Okay, let's deliver the 4. X squared to the 4 is x to the 8. Multiply powers. Negative to the 4 becomes positive, and 5 squared to the 4 becomes 5 to the 8. Finally, y squared to the 4 is y to the 8. That's our final answer. Did you get the same? If yes, that's wonderful. If not, look for an error and fix it. The next example looks really big, but let's be patient. Every single step is just one step at a time, is just one rule that we apply. So, what I would do, as usual, get rid of all negative exponents by switching the level inside those big brackets. So the first bracket is a to the 6 and 2 in the bottom, and then b squared goes down and a squared goes up. Everything to the negative 1 times another bracket, 6 and a 5 for sure. Now a squared goes down, b to the 4 goes up, everything to the 2. And finally, 2 and 3 stays where they were. B goes down, this b squared goes up, and a squared stays up, because the exponent was positive, and to the negative 1. Okay, so now let's collect powers with the same basis. So the first fraction would be a to the 8 over 2b squared, everything to negative 1. In the next bracket, there is nothing to simplify, so we can actually deliver the 2 already. So it is 6 squared b to the 8, remember multiply exponents, and then it's 5 squared and a to the 4. And the third bracket, we can reduce 1b from here and 1b from there, so we end up with 2ba squared over 3, and everything is raised to negative 1. Okay, now it's time to deliver those exponents negative 1, which means take reciprocal. So we can write 2b squared over a to the 8 times. There's not much to do here. The only thing that I could do is to split 6 into 2 times 3. So instead of writing 6, I can write 2 times 3 to the 2. Why? Just because we wanted to keep every number as a power of prime numbers. So in the next step, I would distribute the exponent to the 2 and 3, and possibly simplify or cancel with some other powers of the same basis. So we have b8 here, 5 squared a to the 4, and the third fraction we need to take reciprocal of it, so it will be 3 over 2ba squared. Great! So now what's left to do is to simplify powers with the same basis. For example, let's write all the numerical values first. I have 2, I have 3, so 2 times 3, and here I have 2 squared and 3 squared, times 2 squared times 3 squared. Great, then I have b squared and b to the 8, so it's b to the 10. In the bottom, I have this 2 and this 5 squared, 2 times 5 squared, and then I have a to the 8, a to the 4, and a squared. So 2 plus 4 plus 8 is 14, a to 14, and a single b. Everything is put together, great. Now it's the pleasurable part. Cancel whatever is common. So we can cancel 1, 2, we can cancel 1b, leaving us 9b's in the top, and there is nothing to cancel with a or 5. So that's nearly the end. We have 3 times this 3 square, so it's 3 cube. But let's start with 2 first. So 2 square times 3 cube times b to the 9 over 5 square times a to 14. And that's the final answer. There's nothing else to do here. Obviously, if someone wants to evaluate those numbers, that's okay as well. That will be 9 times 4, there will be 36b to the 9 over 25a to the 14. Both forms are fine for the final answer. And here we have slightly different type of questions. We use exactly the same rules. However, as you see, the exponents contain expressions. They are not just single numbers, but expressions. That's okay, as long as we keep the same rules. So, when we multiply powers with the same bases, we're supposed to keep the base and add exponents, no matter how ugly they may be. So, let's follow the rule. 2a plus 1, first exponent, plus the second exponent, a minus 1. Here I didn't have to use the bracket, but I placed it in a bracket just to indicate that that's the second exponent. Okay, so now what's left to do is to simplify the polynomial that we see on exponential level. We have 2a plus 1a. Oh, that's 3a. And then we have plus 1, and then we have minus 1. This plus 1 will cancel the minus 1. So overall, that's our final answer, x to the 3a. Similarly, if we divide powers with the same bases, we keep the base and we subtract exponents as they are. So the top exponent is 2m, then we have minus because of the division, and then we need to subtract expression with 2 terms. Because there's 2 terms, it is really essential that we put a bracket here, m minus 1. So remember, when you have a minus and something bigger than one term coming up, it has to be a bracket around. Okay, let's simplify this. That means we'll have y, and now release the bracket, we'll have 2m minus m, and remember, switching the sign, plus 1. So altogether, the final answer is y to the 2m minus m is 1m and plus 1. That's the overall final answer. And lastly, we may need to apply the rule of power to the power. When we take power to the power, remember, we multiply exponents. So keep the base t, and on exponential level, we are obligated to multiply a plus 1 times a minus 1. But I hope you noticed that a plus 1 times a minus 1 falls into certain special formula. That's exactly difference of squares. So we can fold it back to the difference of squares formula, a squared minus 1. I hope you remember this formula from previous course, but if you forgot, you can just FOIL this bracket and convince yourself that this is really equal to a squared minus 1. Here we go. That's the final answer.